So I want to introduce the definition of function and get us started on this next section. And I'll probably try to prove theorem 49 today, and then we'll get to the meat of it next week. So this is kind of what everything has been building up to. Probably functions are the most important concept in the entire course. And after this definition, we're going to spend most of our time after this pretty much working with functions. So in the definition, you see that we're defining what it means to be a function. So in some sense, I'm introducing a kind of formal syntax, semi-formal syntax, where I'm introducing the predicate is a function. I'm saying anytime you put a term and then say is a function after that, then what you have is a proposition, a sentence. So then I'm defining that proposition, and I'm using an if and only if to make that definition. Just like, when I define the proposition A subset of B, I use if and only if, and I tell you what exactly it means. It's the same deal here. So here's what it is. So I've written it out here in one way. F is a set of pairs, and this big quantifier with 3 variables. So F is a set of pairs, and for all x, y, z, if the pair xy and the pair xz are in F, then y equals z. Now, is a set of pairs, that's something we defined at the end of the last video. So you saw that. That was some other statement involving a couple of quantifiers. How about this? So what is this trying to say? What does this mean? Well, we could try to read it without mentioning bound variables, and it's going to be a little bit awkward the first time through. So maybe you would say, anytime you have 3 things, if the first thing and the second thing, and the first thing and the third thing, when paired up, are elements of F, then the second thing equals the third thing. Okay, that was weird, and I don't understand anything from it. However, here's maybe a smoother way of saying it. Anytime you have 2 pairs in F whose first positions are the same, their second positions, which are these y and z, must also be the same. So this says anytime you have 2 pairs in F with same first position, then they must have same second position. So the idea when you've got a function as a set of pairs, so the idea is, like if F is a function, then the idea is that it's a set of pairs. So if you were to list the elements, which they might not be listable, we don't know that F can be written as a finite list of elements, but let's just imagine. So I'm writing this in green. That means this is loosey-goosey semantics, not the formal syntax. So F is a set of pairs. Maybe there's some other stuff in there. The idea is that it is when you think of it as a function, the idea is that it is an input to output mapping. So it associates some inputs with some outputs. And the way in which this is formally achieved is that the first positions of pairs are thought of as inputs, and the second positions are thought of as the associated outputs. So if I just use the word input to refer to the left-hand component of any pair that is in F, and the word output to refer to the right-hand component of any pair that is in F, then here's a way to read this. Is it says, anytime you have an input getting associated with 2 outputs, y and z, it must be that the outputs were the same after all. So if the same input, if you have the input x get associated by F to potentially 2 outputs, y and z, then in fact it had to be the same output. Another way of putting it, to every input, F associates a unique output. So these are all fine ways of saying things as long as you agree that the word input is just referring to left-hand positions of pairs that are in F, and the word output refers to right-hand positions of pairs that are in F. Sometimes this this three variable quantified condition, sometimes this is referred to as the vertical line test. And if you think about it, it is basically the same as the vertical line test that they tell you about in high school or whatever. But definitely don't call it the vertical line test, because there might not be any actual vertical lines involved. Instead of calling it the vertical line test, we call it being a function. That's what it means to be a function. So what we're doing is a lot more general than the kinds of functions that you may have looked at in grade school. Functions can take as their inputs really any kind of thing anything that can be written as a term. Anything you can refer to and that is a mathematical object can be the input of a function. And anything that you can refer to can be the output of a function. So it doesn't have to be numbers being mapped to numbers. Literally anything could be getting mapped to anything. This is very general. So another thing is, if you're used to every time you think of function, you think, oh, something that I can plot, well then you're stuck in sort of the number way of thinking. That's just one very, very special example of what a function could be. That's where it's associating some numbers to some other numbers, and you only allow numbers to go here. But the idea is really much more general and much more powerful. Okay, now I want to look at Theorem 49 and proving this theorem. This will be, we will not use this theorem, you will not use this theorem much except insofar as it powers Theorem 51, the essence of function evaluation, which is what you will be using all the time. But to understand what's going on with functions, and to understand the importance of this definition and how it works to achieve what is needed, we need Theorem 49. So this will drive the essence theorems later, which is what you're going to use. So let's do Theorem 49 today. So one way that I've said that you can read this is that it says if you have some input, anytime you have an input x getting associated to two outputs y, they were in fact the same output after all. So to every input, there's a unique associated output. Then if I use that input-output terminology to describe this set that's showing up here, how would you describe this set? So let's read this in English. Let's see. So first let me read it mentioning the bound variable. This is the set of y's such that the pair xy is in F. Okay. Now let me read it without mentioning the bound variable y. It's the set of things such that the pair x comma that thing is in F. Let me try to phrase that a little bit more smoothly. It's the set of possible second coordinates for pairs where the first coordinate is x, for pairs that are in F where the first coordinate is in x. Okay, now let me redo this but using the input-output terminology, where I use the word input to refer to the first position of a pair in F and output to refer to second positions. This would be the set of outputs that F associates to the input x. Let's get that in writing. So we think of that set as the set of, you see x is not a bound variable, so this really is referring specifically to something having to do with x. This is the set of outputs that are associated by F to the input x. So this is really something about x, it's not about y. Y is bound here. And then Theorem 49 is simply saying that if f is a function and x is in the domain of that function, then this set is a singleton, has a unique element. So remember, is a singleton means there exists, for this thing, it means there exists some z such that this could be written as, such that this set here equals singleton z. That's what it means to say it's a singleton. Okay, so theorem 49 is telling you that if you think about is a singleton, if you rephrase that in terms of existence and uniqueness, using this idea from theorem 25, that a set is a singleton if and only if it has a unique element, then theorem 49 is saying if you have a function and you have something x in its domain, then this set has a unique element. In other words, there is a unique output that is associated by f to the input x. So like I said, this theorem will be used to power the sort of essence of stuff theorems coming later here, mainly this one. So pay attention to the hypotheses of this, meaning the assumptions needed to make the theorem work. You need f as a function and x is in the domain. So you'll see these hypotheses show up a lot since that theorem is getting used. So you see later on, f is a function, x is in the domain. These kind of assumptions need to be made to make later things work. See? Function, things being in the domain. Let me find another one. Maybe that's it. Oh, there's one. Function, thing in the domain. Yeah, you'll see it show up a lot. So these hypotheses, this is the first time we work with them, and they'll show up a lot. So this is kind of an important step for us. Okay, let's prove this, and then I'll call it a day for this lecture. So I'll start by assuming so this is an if-then, so I'll assume the hypotheses. Assume f is a function and x is in the domain of f. Now I want to prove that this is a singleton. Well, I'm not going to get anywhere if I don't know what it means to be a singleton. So I go back to the definition of is a singleton. To be a singleton means you can be written as singleton something. So it's an existential statement. So my goal is to prove that this can be written as singleton something. Now, I have a nice way to actually prove that something is a singleton rather than having to work with the definition of singleton directly. Theorem 25, which we proved before in lecture, a set is a singleton if and only if it has a unique element. Having a unique element, so S has a unique element, is formally expressed like this, by this statement. So this is my goal, except with, instead of S, this thing. Actually, so that I don't have to keep referring to this thing, how about I call it S? You're always allowed to do this in your proofs. If there's a long thing that you don't want to keep rewriting, you can just say let, and then give it a name, and then use that name to refer to it as a shorter name. So let's just call this S. Then my goal is to prove that S is a singleton, but I've now rethought about my goal. I have an easier way to do it, which is to prove this. So my goal is to prove that there exists, and let me copy things over here. Should I use x? No, x is already in here as a free variable, not bound. You see, x is getting mentioned here. So I should definitely use something different. Let me start by using just some new variables. So how about a? So there exists a such that a is in S, and for all y, are there y's here? Well, there's no free y. The y is bound, so there's no danger formally in terms of using y here, so that's fine. But I'm afraid of possibly confusing myself and thinking that those y's are going to end up playing the same role later when they are free. So let me just use a different variable. That'll save me the trouble. So for all b in S implies that b equals not x, but whatever I used back here, a. Okay, so hopefully if you read this to yourself, it is intuitive to you that it says S has a unique element. There exists something which is an element of S, and if you had another thing that you thought was an element of S, then that was actually just your first thing. So that's my goal. So then my goal is to prove a certain existential quantifier, right? So which quantifier rule would we use for that? Existential generalization. I want to prove that there exists an A such that blah, blah, blah. Okay, this is the third time we're in this situation in this lecture today. To prove that there exists an A such that blah, 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 we must find an A such that blah, blah, blah. So my goal, let me write it in sort of simpler terms. My goal is to find an A such that this stuff holds. Find an A such that this stuff holds. All right. How am I going to do that? Find an A that is an S? So S is this. How do I find something in there? How do I know this is not empty? Maybe it's empty. Like, okay, I want to find something in there that also satisfies this additional property, but how do I even find anything in there? Maybe it's the empty set, right? Okay, so at this point, it's natural to feel stuck. And so what I do when I'm stuck just thinking about the goal is I look at what I have and see if I can break it down at all. So there's always these two things that are happening at the same time. Taking your assumptions and trying to manipulate them and break them down and unpack them, and at the same time taking your goal and trying to express it in different ways to see how you can get there. And eventually your hope is to make them meet in the middle and then go write your final draft by taking the perfect path that you have found from beginning to end. So, okay, f is a function. Can that help me in any way? My immediate thought is I want to just at least show that there's something in S. Then I'll think about if I can show that there's something that has this additional property. Can I even find anything in S? Will f's being a function help me find something in S? I mean, f being a function means two things, right? It means f is a set of pairs, so every element of f is a pair, but that doesn't tell me that there are any elements of f anyway. So that definitely doesn't tell me that there are any elements of S. And it also tells me this thing, which is also a statement about every element of f, which again does not tell me that there are any elements of f. So that's not so helpful right now for finding something in S. This, on the other hand, might help. So let me just unpack this and see where it takes me. This goal statement is not going to be part of my proof. I'm just going to keep it floating around here. So now I'm going to work on unpacking this. X is in the domain of f. Since x is in the domain of f, so if I just write out exactly what that means, it means there exists a y such that the pair xy is in f, right? That's by the definition of domain using axiom 5. But what I would do immediately after that is use existential instantiation and say we can now get a y such that the pair xy is in f. So let me just skip to that part. As I've said, people often do. We can get a y such that the pair xy is in f. Okay, now we're getting somewhere. Since the pair xy is in f, wouldn't you say that y is an element of S? That's actually what it means to be an element of S, right? Then y is an element of S. This is just using axiom 5. So now I've got something that might play the role of the A that I want to find. Y. Y is in S. does y satisfy this property? That would be nice. So let me just go ahead and see if I can prove this. So again, this will not be part of my proof at the end. It's just the goal that I'm keeping in mind. So now this is my goal. Can we prove this? For y, I mean. By for y, I mean for y in place of a. Can we prove this for y in place of a? So let me just rewrite it instead of being confusing. Can we prove that for all b in S implies b equals y? So this is my new goal. If I can prove this, then I have found an a such that blah, 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 namely a equals y. So to prove this universal generalization, right? Consider any b in S. So consider any b, now assume b is in S. Actually, if I just start writing that, then probably the poor reader of this proof will be confused as to why I'm doing that. So maybe it would be good to point out what we will do. We will now prove, I hope we will now prove successfully that for all b in S implies b equals y. So here's a situation where it makes a lot of sense to state what your goal is. So now it's very clear to the reader why I'm saying consider any b in S. Can I prove that b equals y? So let me unpack b being in S. S is this, so since b is in S, the pair xy is in, the pair xb is in F, right? So that's just axiom 5 again. And now look at what we have. So we have the pair xy is in F, and the pair xb is in F. And F is a function. F is a function. So F is a set of pairs, and this. Anytime you have two pairs in F where the first positions agree, then it follows that the second positions agree. Here are two pairs in F, xy, xb. The first positions agree, it's x in both cases. Therefore, since F is a function, the second positions must agree. Since F is a function, let me get this junk out of the way. Since F is a function, and these pairs are in F, we have, this is a universal instantiation, what I'm doing. So this is a universal statement. Anytime you have this, you have that. And this is one particular time. So this is universal instantiation. We have y equals b. But that was my goal, right? Which just went off screen. To show that every b in S is y. So for all b in S implies b equals y. That's what we just showed. So let's see. So I've succeeded in proving this segment. So maybe this could stand to be better organized. I think what I will do is move this stuff to be its own claim. Hang on, let me do this off screen. So we'll move the scratch work down there. And this deserves to be its own claim. And, you know, instead of saying we will now prove, how about I make it a claim inside my theorem. So I claim that this is true. And here is the proof, the very short proof of the claim. So that's a little bit better organization there. So that's its own thing. So now we've got y in S, that's here, and anything in S is just y. We have proven that, basically proven this kind of statement about S, right? So we've proven that S has a unique element. Therefore, by theorem 25, it is a singleton. Remember, being a singleton is not defined to be having a unique element. Being a singleton is defined to be, you can be written in this form, but theorem 25 links the two ideas. So by theorem 25, S is a singleton. And that finishes the proof, and now I can do away with this scratch work. So the goal was to prove this thing is a singleton, right? So that's done. So what this enables is anytime you have f a function and x in the domain of f, so here's the new power that we have now gained. Anytime f is a function and x is in the domain of f, we have that set is a singleton. So we have that there exists some, being a singleton, there exists some x, except I'm not going to call it x since this is x, so there exists some y, say, such that the set of y's that get associated to the input x is actually just singleton y. So, in other words, our power is we can get a y such that this happens. Such that the set of y's that get associated as the outputs to the input x is actually just singleton y. This means we can apply this occupant idea to this thing and extract the unique y which gets associated to x. That is what we refer to, so if we do that, that is what we refer to as f of x. F of x is the unique y that gets associated to the input x. So this theorem enables that. Okay, so we'll start next time with the definition of f of x.